So continuing on with energy, today level 2 NCEA physicists in mechanics, we'll look at the relationship between work and energy. Okay, so describe a joule in terms of fundamental SI units. So a joule is going to be equal to the idea of work equals force times distance. Okay, so work will be newtons times meters. So where does newtons come from? Well, force equals mass times acceleration. So newtons equals kilograms times meters per second per second. So therefore, if we substitute kilograms meters per second into newtons, a joule will be kilograms meters squared times, or per second. Okay, so kilogram meters squared per second. Now, let's consider what a watt is. What a watt. Okay, so a watt is going to be joules per second, or joules to the s to the minus 1. Power equals work divided by time. So therefore, since work is in joules, and we just worked out what the fundamental units are for a joule, a power will be kilograms meters squared per second divided by seconds. Okay, which will essentially mean it'll be kilograms meters squared divided by seconds cubed. And if you rearrange, that will be kilograms meters squared seconds per second. There we go. So work and energy are related. Okay, so distance equals v squared over 2a when you ignore the initial velocity. Work will be force times v squared, or final velocity squared, over 2a. Therefore, work equals mass v squared over 2, or half mv squared. Ooh, that sounds familiar. Okay, and work in the second example is half f delta x, which equals half k delta x times delta x, or half k delta x squared. Oh, that also looks very familiar, doesn't it? Okay, it's a potential energy, of course, in a spring. And work, of course, equals force times distance, which equals mg, okay, in terms of this ladder, times delta h, or mg delta h. Oh, the potential energy in a gravitation in a height on an object of a certain height, gravitational potential energy. Okay, so there's an interrelationship. So in terms of energy conservation, energy is still conserved. Okay, you can't create or destroy it, but it does transfer in and out of systems. Okay, so electrical energy, for example, can be converted into sound energy in a speaker system. But the example I've got here is that when you lift a 10 kilogram child with 98 newtons of force into a high chair of 0.75 meters above the ground, your work is adding to the potential energy of the child. Okay, so the initial potential energy will be 0. The work of lifting will be work equals force times distance, which equals 98 times 0.75, which is equal to 73.5 joules. And then looking at the change in potential energy, that will be mass times gravity times change in height, which is 10 times 9.81 times 0.75, which is, lo and behold, also 73.5 joules. So you've done work to bring the child up to the top of the high chair. And then you've also got to think about kinetic energy. So again, energy is still conserved. It's just being turned into a different form. Okay, so when a 40 kilogram kid runs 5 meters per second and slides to a stop, his initial kinetic energy is lost to the work of friction. Okay, so his initial kinetic energy is half mv squared. Plug the numbers in. There'll be 500 joules. The work of the friction will be minus 500 joules. Therefore, the total kinetic energy at the end will be 0 joules, because you've got 500 plus minus 500. In terms of conservation with work, so work is creates energy, and energy allows work to occur. That's the relationship between the two. And of course, there are always two ways to solve problems. Okay, so looking at this example here, you can either use a kinematic equation where acceleration equals force divided by mass. Okay, F equals ma, just rearrange that equation. So the acceleration will be 0.5 meters per second. then the distance will be 50, initial velocity will be 0, of course, and the acceleration is 0.5 meters per second, which is as calculated. Use the equation of Vf squared equals Vi squared plus 2AD. Plug in the numbers, you get an answer of 0.07 meters per second. Using the concept of energy, the work is force times distance, which equals half mv squared. 1,000 times 50 equals half 2,000 v squared. Rearrange, and v squared, take the square root of it, and you get v equals 7.07 meters per second. And that's just an example of how you can solve problems in more than one way in physics.